Hello everyone. In this video I'm going to show you how the internet works, and without assumptions that you know anything about the internet and about modern computer networks. You will learn the basics of IP routing, how the internet is organized in the background, about servers and about data centers, and what routing protocols make the internet possible. The first concept that I want to address is client-server architecture. Client-server architecture is a computing model where tasks are divided between service providers or servers and service requesters or clients over the network. Any client in the world, when they're using some service, they have a session with a remote server that is located in some data center. And for any resource from that server, they need to request it via specific request packets for that protocol. For example, for YouTube or Netflix, that would be HTTP protocol. For WhatsApp, there would be protocols for call managing like session initiation protocol or real-time protocol. This means that any app that we're using on our device, it does not have any kind of special intelligence or special capabilities. It only has enough code to display the resources from a remote server on places that were predetermined by developers. For example, profile pictures, comments, number of likes, etc. And client-server architecture is not something that we have to explicitly strive to build. This is because when you have a server and when you have a service, this already implies that you have a client somewhere. So client-server architecture is already native to all of our applications. Here we can see another good representation of the client-server architecture. Let's say this person wants to connect to her home router and access the internet. The first packet on the network would be by her laptop to try to discover so-called DHCP server. And her device would ask, is there a DHCP server on this network? And DHCP server, which is a service running on her home router, would reply and say, yes, I am the DHCP server. Here is your IP address. Here is your subnet mask. Here is your DNS server, which is me, also a service running on a home router. And here is your default gateway, which is also me. So this person is already a client of a DHCP server. Let's say that she wants to access Facebook.com. She will need to send an HTTP request to Facebook.com's IP address. In order to do that, she will first need to find out the IP address of Facebook's server. So she will consult with her DNS server, which is a service running on her home router. She will send a DNS request and ask, what is an IP address of Facebook.com? When she receives the IP address back, she will be able to fire off this HTTP request to her default gateway. Her home router will forward this packet, and the packet will travel across many internet service providers to reach Facebook's server. Facebook's server will send an HTTP reply. The reply would take the same path back, and the web page will eventually load on her device. So here we can see only in order to load a simple web page to your laptop, you have to be a client of multiple servers. And there is a server for everything. For everything that we use on the internet, there is some server that makes it possible. And since we're talking about servers and data centers, why not show how data centers look on the inside and how servers actually look like? Here we can see a typical data center. Servers are installed in these things that are called racks, and these servers have a form that is called rack server. When you install them, you can push them in and pull them out when you need to replace some defective hardware. On the floor, we can see some holes, some grid. This is called cold aisle. So you would push out cold air through these holes. The servers would take in this cold air, push it over the components that are emitting heat, and push out the warm air in the warm aisle. You can also notice that these rack servers have different height, and the height of a server is measured in so-called rack units. So we can say that these servers have 1 rack unit of height. This server probably 3 rack units, and this one 4 rack units. In the back we can see the cabling. You can find cables like power supplies and network connections. Data centers are built to sustain earthquakes, to sustain attacks, floods, etc. They also have power redundancy and uninterrupted power supplies. So if power supplies were to fail here, and a UPS, an uninterrupted power supply, would take over the workload for let's say 10 or 15 minutes until diesel power generators would boot up and start to provide power to a data center. And on this picture we can see a representation of a usual rack server. This rack server has one rack unit of height. In front you will normally find SSDs or hard drives. Then you will find a fan cage with field replaceable and hot swappable fans. These things pull the cold air from the cold aisle, push it over the components to take away the thermal energy and push it out in the hot aisle. Here are the RAM modules and some more RAM modules. And normally in rack servers you will find two CPUs that are installed under a heatsink. Between this heatsink and actually the CPU you will find thermal paste. This paste is really good conductor of thermal energy and is able to pull this thermal energy and to radiate it using this heatsink. In the back you will normally find redundant power supply units. They also have internal fans that are helping to maintain the good airflow in the server. And finally we came to our representation of the internet. So let's see how it works. We already talked about client-server architecture and how all resources that we request, they are running in remote data centers on some servers. Here you can see data center of Facebook. Here you can see data center of YouTube. Here you can see the data center of Netflix. And the clients are scattered all around the world. We also can see these AS numbers or autonomous system numbers, but I will talk more about it later. The most prominent thing on this picture is BGP. And this is actually kind of the main character of today's video, and BGP is what makes the internet possible. So what is BGP and why is it so important? So let's say that you are a service provider like YouTube.com. It is in your interest that the entire internet knows where to reach the IP addresses of your servers. And in order to accomplish this, you will form so-called BGP neighborship with multiple internet service providers. You will advertise these IP routes to your internet service providers, and they will do the same with their neighbors. In no time, this IP information will propagate throughout the entire internet, and the whole world will know how to reach your servers. And this is crucial in our client-server architecture that we discussed. BGP is a routing protocol. It lets us configure our networks and exchange IP reachability information across the networks. But as a beginner, I oftentimes wondered, why can't we just plug in routers to one another and just let everything work out by itself? As it turns out, this is not all that simple. Let me show you what it takes actually to build IP reachability and what routing protocols do to help us achieve this more practically. Here we have 4 routers, and we can say that all these routers are under our administration. If we wanted to create IP reachability between all the routers in this network and without using routing protocols, we would need to configure so-called static routes on every single one of these devices. And we will need to literally tell to every single router how to reach every single network that is depicted here, or any new networks that will emerge in the future. So on router 2, for example, we would need one static route for this network and one static route for this network. We can say that one link is a one network. On router 4, we will need static routes for this network and for this network right here, etc. You can see this is already impractical and not scalable. Not to mention that if any of these routes were to go down, you would have no convergence. You would just black hole your traffic and you would not be informed that that link is down. This is where routing protocols come to rescue us. There are many routing protocols, and some of them are used between the so-called autonomous systems and some of them are used within. But for sake of this conversation, we will say that we're going to configure BGP process on all of these routers. And the BGP is a protocol which will exchange IP reachability information between all of these routers, and it will also inform the neighbors if any of links were to go down. So the neighbors can purge these links from their routing tables. By doing this, we achieved automatic IP reachability information and convergence in case that any of the links go down. Now let's see how we would configure BGP in practice and what are autonomous systems or autonomous system numbers. Let's say that you are a customer here. You are a customer of your internet service provider and you have some servers and some services running here, and you want clients that are possibly all around the world to be able to reach these servers. You would configure BGP neighborship to your internet service provider, and here we can see autonomous system numbers as native part of BGP as a protocol. When you configure BGP neighborships, you would not only configure BGP neighborship to the IP address of your internet service provider. You would literally say, I want to build BGP neighborship with this IP address and with this autonomous system number. In this case, autonomous system 100, autonomous system of our internet service provider. And the ISP will do the same thing. They will configure BGP protocol and form neighborship with your IP address and with your autonomous system number. If you wanted to make this link a bit more resilient, you would have so-called dual home scenario. You will have two links on two different routers to the same internet service provider. This scenario here is a bit more resilient. You would have a single link, each leading to a single service provider. Again, to their IP address plus autonomous system number. IP address plus autonomous system number. And probably the most resilient scenario for a small customer would be a dual multi-home scenario. So you would configure two BGP neighborships to two different internet service providers. But a really important thing here is that autonomous systems are native parts of BGP protocol, and you need to include your autonomous system numbers in many packets that are sent by BGP protocol and that are received by BGP protocol on your routers. But how do you actually get an autonomous system number? Well, it turns out there is a global organization called IANA. IANA does allocation of internet number resources to regional internet registries. We have almost one per continent. IANA would allocate large IP address blocks to regional internet registries. It would allocate autonomous system numbers to them. It would manage the global DNS root zone or maintain key internet protocol registries like port numbers, protocol parameters. So in order to get an autonomous system number, you would go and contact your regional internet registry and request one. And I want to emphasize here that if you are a casual user of internet, you do not need an autonomous system number. Most of the users on the internet do not have and do not need an autonomous system number. You only need access to the internet. Autonomous system number, you will need it if you want to be, for example, an internet service provider, or if you want to be a service provider and publish your application in some data center and you want to advertise this to multiple ISPs in your region. So for example, you would go to the web page of your regional internet registries and find a web page where you can request an autonomous system number. Here we can see some explanations. This form can be used to request an autonomous system number for your own infrastructure or on behalf of a customer. For example, your ISP can request an autonomous system number in your name. An autonomous system is a group of IP networks run by one or more network operators with a single, clearly defined routing policy. This is really important to emphasize, routing policy. Without an autonomous system number, if you are a casual user on the internet, or you just have some kind of virtual server with some cloud provider with a public IP address, you cannot enforce any routing policy if you do not have an autonomous system, because even if you have a public IP address, you're not really taking part in the internet. You're only using the internet or publishing a service on some public IP. In addition to the basic requirements, you must provide at least 2 autonomous system numbers from your peering partners. This means that you are peering with at least 2 other autonomous system numbers, for example, 2 internet service providers. And in order to do this, you don't have to be some kind of a big fish or have a big data center. It's enough that you have a router with 2 uplink interfaces and you connect to 2 internet service providers and you pay for 2 dedicated links. That's it. And if you would like to learn more about BGP as a protocol, there are great websites on the internet, for example, bgp.tools. Here you can search by autonomous system number, search by prefix or IP address, search by DNS, or even MAC address. And you can get an abundance of information about autonomous systems, for example, how they are peering, how many peers they have, how many transit networks they have, etc. Now, the task of BGP is not merely to exchange IP reachability information across the internet. Routing protocols have many other tasks to accomplish, and one of the most important tasks that BGP has to accomplish on the internet is to prevent so-called routing loops. You see, every route that you advertise to some ISP, to some other autonomous system, this route can actually come back at you, and if the routing protocol does not have a coping mechanism to cope with routing loops, your autonomous system would be confused and would not know where to actually reach this specific prefix. Should it go this way, or should it go this way or this way? And let's see how BGP does this. Let's say this is a tiny portion of the internet, multiple autonomous systems. And let's say that this specific autonomous system wants to advertise these IP prefixes to their neighbors. This long form of IP addresses is called IPv6. It is 128 bits in length in comparison to IPv4 that many people are used to. There are 32 bits in length. As this autonomous system is advertising this IP prefix, it will not only advertise the IP address, it will also add attributes to this route, and one of the most important attributes is called AS path. As this route exits the autonomous system, the router will append its own AS path to the route to let the neighbor know which autonomous system this route originated from. The route will be saved in router 4's routing table, and it will be forwarded to the next neighbor. Upon exit of this autonomous system, the router 4 will also append its own autonomous system number in form of AS path attribute. So when the route arrives on this router right here, it will already have two autonomous systems in AS path attribute. And the same continues on every hop. Let's now say that this specific route is advertised by router 3 to router 4. When router 4 reads this update, it will see this specific IP prefix and it will check the AS path attribute. Now the loop prevention mechanism will kick in. The router 4 will see its own autonomous system number in the AS path attribute, and it is a standard implementation of BGP that if a router sees its own autonomous system number in an update, it will automatically discard this route. Why? Because this route already passed once through me. If I were to take it in my routing table, it would create a routing loop. And AS path is not the only attribute that BGP uses. BGP is a really robust routing protocol, and actually the only routing protocol that can support the internet. It has many BGP attributes. Some of them are more important, some of them are less, but they all allow us to enforce our routing policy between autonomous systems. For example, well-known attributes, they must be included in every update, they must be understood by every router, and they're advertised between autonomous systems. Well-known discretionary, they do not have to be included though. With optional attributes, we have so-called transitive and non-transitive attributes. They do not have to be included in updates, they do not necessarily need to be understood, but transitive attributes, they are advertised between autonomous systems. And all of these attributes help us do traffic engineering between autonomous systems. And I already mentioned a few times that BGP is normally used between autonomous systems and that other routing protocols are used within autonomous systems. And here we can see multiple autonomous systems with BGP neighborships between them. The interesting thing is that within autonomous systems, we use routing protocols like EIGRP or OSPF. EIGRP and OSPF are considered to be internal gateway protocols, and BGP is considered to be external gateway protocol. And there is a fundamental difference between the EGPs and IGPs, how they form neighbor relationships and how they scale. Internal gateway protocols, they scale really well within autonomous systems, and BGP scales really well between autonomous systems. Let's again say that we have an autonomous system and we will configure OSPF on all 4 of these routers. What we would literally do is go to this router and configure so-called OSPF process and advertise any routes that we are connected to, any networks that we want to advertise to other routers. By doing so, our router will start listening on so-called multicast IP addresses that are reserved for OSPF as a protocol. So 224.0.0.5 and 224.0.0.6 for OSPF. The IGRP has its own reserved multicast IP addresses and other protocols also. If we do the same on other routers, every single router would start listening on these multicast addresses, will start listening for updates, and will start to send updates to those IP addresses. And in no time, we would actually have real IP reachability between all these routers to any networks that they advertise to one another. And I put this switch in the middle on purpose. I wanted to emphasize that multicast IP addresses are only used within the same so-called broadcast domain. We can see here that all 4 routers are on the same network. They have the first 3 octets the same, so /24 subnet mask. That means that every interface here is on the same broadcast domain and also on the same multicast domain. And with OSPF, all of these routers will make kind of a database of all the interfaces in the network. So they will know the state of every interface within this network. This is really good for autonomous systems, but this is really bad for the internet between the autonomous systems. On the internet, you do not need to know necessarily the link states of every link of every router for every autonomous system. This is impossible, impractical, and makes no sense. This is why OSPF is also called link state routing protocol, and BGP is called path vector routing protocol, and I will talk more about it later. Now with BGP, there are no multicast IP addresses. BGP uses so-called unicast IP addresses. This means that for every single one of these routers, you will need to form 3 neighbor relationships. One to the unicast IP address of this router, one to the unicast IP address of this router, and one to the unicast IP address of this router. It's the same for all other routers. And with BGP, there are no multicast IP addresses reserved for it. BGP uses what is called unicast communication. So if you wanted here as router 1 to exchange routes with all these routers here, you would need to create a single BGP neighborship with every single one of these. And it goes for every other router. If they want to exchange IP reachability information, they need to create unicast IP neighborships. That's why BGP is mostly used between autonomous systems, and other protocols like OSPF and EIGRP are used within autonomous systems. You could actually with BGP configure something that is called route reflector, and this would allow you to create IP reachability without having to configure full mesh topology. But this is a niche application, and normally for internal gateway protocol, you would go with OSPF or EIGRP. And because you do not know with BGP link states of every single router of your neighboring autonomous systems, and you only know the next hop for some prefix, you only know next hop to reach youtube.com. BGP uses something that is called routing by rumor. So when you advertise a route to your neighbor, you say you can reach this IP through me, and BGP takes it and believes it, and this is why it's called routing by rumor. Now I also put these things here. These are called commercial internet exchanges, places where many autonomous systems, ISPs, would network together to create peerings, to use each other's networks for transit, and so on. And these are the actual autonomous system numbers of Facebook, of Google, of Netflix, and you can search them in, for example, bgp.tools or some other BGP tool that is out there. So we learned here the basics of client-server architecture, how every server is located somewhere in a remote data center, and how in order only to load a simple web page on your device, you are a client of multiple servers. We learn about data centers, what are racks, what are rack servers, and rack unit heights, what is a cold aisle and hot aisle. We looked at the inside of a rack server and observed the normal airflow in terms of cooling and the most usual components used. We saw how the internet works, how BGP exchanges IP reachability information, and what are autonomous systems. We talked more about BGP attributes and its robustness as a protocol, and specifically how AS path attribute is used to prevent routing loops. We talked about differences between external gateway protocols and internal gateway protocols, so EIGRP and OSPF, and how you would use EIGRP and OSPF within autonomous systems and BGP between autonomous systems. We also talked about how OSPF and EIGRP use multicast IP addresses to exchange IP routes and how BGP uses unicast IP addresses, and why is it so difficult to implement BGP within autonomous system. We mentioned routing reflectors within BGP as a way to avoid having to configure full mesh within an autonomous system, and also why you would still prefer OSPF or EIGRP within an autonomous system. And finally, we talked how BGP does not have to know about link states of every router within every autonomous system of their neighbors. It only needs to know the next hop for some IP address it wants to reach, and this is called routing by rumor. So thanks for watching and see you in the next one.